Hello, everyone, and welcome to today's webinar, Advances in EDS and EBSD. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we will follow up via email after the webinar. The first part of today's webinar is entitled High Precision EBSD from Spherical Harmonic Indexing. This talk will be given by Dr. Gregory Sparks. Dr. Sparks earned his PhD in Materials Science and Engineering at the University of Illinois, Urbana-Champaign in 2019. He studied the statistics and dynamics of strain bursts in microcompression testing of single crystal metals. Since then, he has worked as a postdoctoral researcher on a joint project for The Ohio State University and the Air Force Research Laboratory, implementing advanced SEM characterization techniques into a 3D serial sectioning workflow with the goal of advancing understanding of fatigue crack initiation and growth. His primary research interests are microscale deformation mechanisms in metals and techniques for investigating them. Now over to Dr. Sparks.
All right, thanks for the introduction. Let's see, okay, and here we go. With that out of the way, welcome to my presentation, High Precision EBSD from Spherical Harmonic Indexing. So first, I will give a brief overview of EBSD indexing techniques. Every form of indexing begins with the raw EBSD patterns formed by electrons diffracting from various planes in the crystal, as shown in the figure here. Conventional, or Huff indexing, uses the Huff transform to locate Kikuchi lines corresponding to diffraction from individual planes in the experimental patterns. It then identifies the final crystal orientation based on the angular relationships between these planes as compared with lookup tables generated for specific crystal systems. This approach is fast, easy to automate, and reasonably tolerant of noisy patterns. However, it does not provide impressive orientation precision, typically on the order of 0.5 degrees, give or take a few tenths of a degree. The first technique, commonly referred to as high-resolution EBSD, was introduced in a 2006 paper by Wilkinson, Meaden, and Dingley. Pairs of EBSD patterns are compared using image cross-correlation in multiple subregions, with an example of such subregions shown as the white squares in the figure here. The relative orientation of two similar scan points can be determined with extremely high precision, better than 0.01 degrees in optimal conditions. However, it has difficulties handling large changes in relative orientation, as the patterns will have shifted to the point that there is no overlap for cross-correlation without further processing. It also requires very high resolution and high quality patterns for best precision. Dictionary indexing is an interesting method based on a pixel-to-pixel comparison of each experimental pattern with a dictionary of dynamically simulated patterns, sampled uniformly across the space of all possible orientations. The orientation of the simulated pattern that best matches the experimental pattern is taken as the indexed orientation. While this initial result is generally rather imprecise, on the order of 0.7 degrees, it displays incredible robustness against noise and low pattern resolution, being capable of indexing raw patterns with no humanly identifiable features whatsoever. The orientation precision can also be significantly improved by a second stage refinement operation following initial indexing. However, the brute force comparison is quite slow without throwing a massive amount of computing hardware at the problem. As initially introduced, spherical harmonic indexing was intended as a more computationally efficient version of dictionary indexing with similar advantages of robustness against noise and tolerance of low pattern resolutions. In the following slide, I will go over how it works in more detail. I should also thank Will Lenthy and Mark DeGraff for making their spherical harmonic indexing code publicly available as EM-Sphinx. So in this method, first, diffraction is simulated for every possible orientation of the desired crystal structure with the appropriate sample tilt and electron beam energy for the experimental conditions. Both the simulated master pattern and the experimental patterns are then projected onto a sphere and decomposed into spherical harmonic functions. The cross-correlation between each experimental pattern and the master pattern can then be efficiently found in harmonic space in a manner roughly analogous to finding the cross-correlation of two functions in Fourier space. This initial solution can then be refined using Newton's method to improve the overall precision, as the analytical equation for the cross-correlation magnitude is known but difficult to solve explicitly. This determines the rotation which causes the experimental pattern to most closely match the master pattern and therefore the crystal orientation. So when I initially read about this method, I was intrigued by the paper's description of the precision improving along with the noise tolerance as the conversion bandwidth was increased, so I decided to see just how far I could push it. But before I go further, I should explain exactly what I mean by bandwidth in the context of spherical harmonic indexing. The bandwidth is simply a unitless integer used as a parameter for the spherical harmonic decomposition. Increasing the bandwidth increases the number of spherical harmonic functions summed when converting pattern data into harmonic space, which therefore increases the fidelity of the conversion as the bandwidth increases, as seen in the figure on the left. However, increasing the bandwidth also drastically increases the amount of processing time and memory used to perform this conversion, so it is advantageous to keep it as low as possible. This is particularly true for conversion of the experimental patterns, as each must be converted individually, while the master pattern only needs to be converted once and can simply be referenced thereafter. I refer to the bandwidth values for the experimental and master patterns as the analysis bandwidth and the master pattern bandwidth, respectively. Okay, so as published in my ultramicroscopy paper, exhaustive testing of indexing precision on a single crystal silicon wafer versus the analysis and master pattern bandwidth provided me with several results. First, given high-quality patterns as input, spherical harmonic indexing was easily capable of providing a high level of precision. Note that this entire chart of precision versus bandwidth is below 0.05 degrees. Second, increasing analysis bandwidth did improve precision, but with significantly diminishing returns above a bandwidth value of approximately 120. Finally, at very high analysis bandwidths, unexpected indexing artifacts appeared, involved the indexing orientation of the silicon wafer splitting into two closely spaced yet clearly distinct groups in orientation space, as shown in the figure on the right. This is related to certain high-frequency features that can appear in spherical harmonic reconstructions with higher bandwidths. Thankfully, further testing demonstrated that these artifacts simply did not appear for analysis bandwidths of 123 or lower. As this is already a relatively optimal value, considering the diminishing returns on precision, 123 is now my standard choice for analysis bandwidth. The master pattern bandwidth did not seem to have any major effects on the precision outside of the bimodal artifact behavior, where the presence or absence of artifacts for a given set of raw patterns was dependent on the combination of analysis and master pattern bandwidth. I ended up choosing a master pattern bandwidth of 788 as my standard value to allow for a relatively high fidelity representation of the simulated pattern data. I should note that the precision values shown on the previous slide were taken from a data set with very high exposure time and the maximum available pattern resolution in order to isolate the effect of the analysis parameters on the precision achievable. I went on to examine the effects of camera binning and exposure time on precision while leaving the analysis parameters and the beam current fixed. Results of my testing are shown in the figure and table here, with more details available in my paper. Note that here the precision is the vertical axis, exposure time is the horizontal axis, camera gain is represented by the symbol color, and then the camera binning and therefore pattern resolution is represented by the symbol shape. And as you can see in the figure, clearly the signal to noise ratio of the captured patterns is the critical value, with the precision increasing as the exposure time increases and the camera gain is decreased. Interestingly, I found that this precision is essentially unaffected by the pattern resolution as long as the signal-to-noise ratio remains high. And in fact, at the lower exposure times, decreasing the pattern resolution by increasing the camera binning can actually improve the final precision due to the improved signal-to-noise ratio. Although sadly, that only works with the older CCD cameras. You don't get quite the same effect with more modern CMOS cameras. Now, here it takes a relatively long exposure time to achieve a very high precision, but that's essentially because I used a relatively low beam current here in order to allow reaching such a long exposure time without simply saturating the camera. More recently, I proved my hypothesis that improved scan rates would be possible while maintaining the high level of precision by using an increased beam current. So with a more modern SEM and faster EBSD camera than I used for my initial testing, and an impressively high beam current of 400 nanoamps, I was able to collect data at or above a rate of 3,000 patterns per second, while maintaining an orientation precision of 0.06 degrees, as measured on a silicon wafer sample in an identical fashion to the data shown here. I should, however, note that while the orientation precision is good, the massive increase in beam current will increase the size of the interaction volume and therefore decrease the spatial resolution of the scan. As our current experiments use scan point spacings on the order of 1 to 2 microns, the decrease in spatial resolution was not a major concern for us. However, others wishing to resolve finer features may need further experimenting to determine the trade-offs between the beam current and the spatial resolution. Here, I experimentally demonstrate the reduced orientation noise using spherical harmonic indexing versus Huff indexing. The figures are kernel average misorientation maps from a nickel-based superalloy sample with a 1 millimeter square cross-section. For anyone unfamiliar with the concept, kernel average misorientation, or CAM, is the average misorientation angle between a given scan point and a ring of nearby points, in this case simply the immediately neighboring points, and it's a very commonly used metric in analysis of EBSD orientation data for visualizing local orientation gradients within grains. Any individual misorientations above a certain threshold are discarded prior to said averaging in order to avoid comparing data points that cross grain boundaries. Now, this sample was annealed and not expected to have any significant orientation gradients, but the Huff data still displays significant CAM values due to its general imprecision. While the average CAM using the Huff indexing was 0.36 degrees, when using spherical harmonic indexing on the same raw patterns, the average CAM drops to only 0.057 degrees, matching the 0.06 degrees noise threshold previously identified on a silicon wafer for spherical harmonic indexing under matching conditions. I should also note that CAM values are affected by the scan point spacing since it is a point-to-point measurement. For a real orientation gradient of a given magnitude, a higher spacing will result in higher measured misorientation angles. For this data set, the spacing is 2 microns per scan point, which makes it impressive that the local misorientation measured using SHI is still at the noise floor, calculated from a much more tightly spaced scan on a silicon wafer. As an example of features that can only be revealed by this improved orientation precision, here I show 2 kernel average misorientation plots on the same sample with different polishing procedures. In a previously used experimental procedure, a 150-second colloidal silica polish after grinding with 1 micron diamond was used to produce a good surface finish for EBSD. However, with the improved precision of SHI, I found that this polishing routine actually leaves a small but detectable amount of residual subsurface damage from the grinding process, visible as the streaks of increased CAM in the figure on the left. Increasing the colloidal silica polishing time helped eliminate this and should hopefully ensure that any local misorientations observed using high precision EBSD are inherent in the sample, rather than being artifacts from the sample preparation process. Note that in both the maps shown here, the CAM values observed are all below the noise threshold for Huff indexing, so these features would simply not have been visible in previously without high precision EBSD, and no optically visible scratches were present on the sample surface for either of these cases. You may have noticed that throughout this presentation, I've specifically referred to precision in orientation indexing rather than accuracy. The latter is significantly more difficult to achieve, with one of the primary sources of inaccuracy being errors in determination of the pattern center. This is a numerical value representing the relative position of the scan point from which a given pattern originates and the EBSD detector that captured said pattern, or in other words, the sample detector geometry. The pattern center is generally measured as a triplet of values x star, y star, z star, where the three values are simply the x, y, z coordinates of the interaction volume on the sample, as measured in the reference frame of the detector, where the x and y coordinates are in the plane of the detector screen, and the z coordinate is measured normal to the screen. Note that the sample itself actually has its own distinct reference frame that is used for measuring the scan point positions, also as shown in the figure on the left. Exactly how the pattern center values are numerically defined varies by EBSD manufacturer, but is typical for them to be normalized relative to the size of the detector screen in some way, such as each distance being divided by the detector screen width. Any errors in determination of the pattern center will directly affect the indexed crystal orientation, with small errors causing small orientation shifts, while large errors can cause spectacular misindexing or even complete indexing failure. For conventional EBSD, it is common for pattern center values to simply be taken from stored calibration values at a nominal sample position. These are generally close enough to allow successful indexing. Any inaccuracy in the absolute orientation from differences between the stored value and the unknown true value is simply ignored. This is sufficient for many practical purposes, especially if only using relative metrics such as kernel average misorientation. But 3D data fusion of orientation maps from serial sectioning is an example of where absolute orientations can be important. In the figure on the right, I show a Rodriguez space plot of the orientation shift induced by artificially altering the pattern center y value, x value, or both x and y value by 1,000th of the detector screen width while analyzing a single set of raw patterns from a silicon wafer with spherical harmonic indexing. And since the pattern data here is from a 1 micron square on the silicon wafer, nominally all the orientations are the same, and the small clouds are essentially just the noise floor. So you can see, well, the orientation shift from the pattern center shift is small, on the order of 0.1 degrees in all three cases. It's clearly detectable with this level of precision. This actually makes the high precision EBSD even more vulnerable to pattern center error than conventional EBSD, where a certain amount would simply be hidden within the general orientation error from imprecision. Obviously, some method of accurately finding the pattern center is necessary. It's also important to note that the pattern center changes from point to point as the beam is scanned across the sample surface, so the pattern center shift versus position must also be accurately characterized in order to achieve accurate results. The literature contains a variety of methods for determining pattern centers in EBSD. The most direct is shadow casting techniques that place physical artifacts between the sample and the detector and observe the resulting shadows on collected patterns, but these require inconvenient hardware modifications and can result in the risk of collisions inside the SEM, so they are not commonly used. One popular method is the moving screen technique shown in the figure on the left, where the EBSD detector is retracted to several different distances from the sample and patterns collected at each distance, as this will visibly identify the pattern center as the point on the detector screen around which the rest of the pattern is magnified. Sadly, this technique relies on the assumption that insertion and retraction of the detector is a perfectly linear motion. In fact, it has been demonstrated in the literature that for commercially available EBSD systems, the detector motion is not precise enough to localize the pattern center to the level desired here. It does work, but it's simply not precise enough. Another option is various methods of fitting the pattern center values of experimental patterns versus simulated patterns. Most commercial EBSD packages come with a version of this based on simple kinematic simulations or the equivalent, which is used for calibrating how the pattern center changes with working distance and beam position on the sample. While fast and easy to use, these routines generally do not provide PC localization to better than perhaps 0.5% of the screen width, sufficient for conventional EBSD, but not good enough for our purposes. More advanced dynamical simulation software is theoretically capable of better precision, but while the schematic here is shown as a two-dimensional input space to allow the figure to actually be comprehensible, in fact, it is a six-dimensional and highly nonlinear optimization landscape with 3 variables defining the crystal orientation and 3 variables defining the pattern center coordinates. Worse, even when actually near the true value of orientation and pattern center, the optimization landscape can have very shallow minima in the similarity metric, as the changes in the output pattern from a small orientation shift are very similar to the changes from a small pattern center, although thankfully not identical. Despite these difficulties, in the end, I chose to use fitting versus simulated patterns as my method for finding the detector geometry due to its ability to be applied in post-processing with minimal alterations to the experimental procedure. In particular, I selected a method very recently demonstrated by Zhu et al., which uses a differential evolution algorithm to locate the optimal solution in the complex and nonlinear search space. Mark DeGraff's EMSoft dynamical diffraction simulation software is used to generate the simulated EBSD patterns for comparison. The figure here is multiple views of a 3D scatter plot of my results from 2,500 PC fitting runs on a single experimental pattern, which I used to demonstrate to myself that this stochastic method would converge with sufficient consistency for my purposes. In fact, I actually had to change my pattern acquisition parameters several times to reach a level of consistency I considered acceptable. Once again, the critical factor seems to be the signal-to-noise ratio of the patterns. My final parameters for acquisition were actually identical to my high-speed EBSD scan parameters, but with the addition of 16 times frame averaging for reduced random noise and an additional step of background correction in post-processing. The final consistency in convergence of the pattern center proved to be about 0.06% of the detector screen width, with a corresponding potential orientation error of very roughly plus or minus 0.06 degrees from imprecision in the pattern center fitting, which is thankfully on the order of the noise floor for spherical harmonic indexing. As this fitting algorithm takes a relatively long time for analysis per point, my plan was to acquire a sparse grid of high-quality patterns covering the majority of the sample and then fit the pattern center shift versus position using the results across this grid, which allows characterization of the PC shift for the true surface orientation of every sample scanned, as opposed to the conventional method of calibrating the PC shift geometry once and then applying it to every dataset uniformly. It also provides redundancy against the occasional bad fit from a pattern acquired in a grain boundary overlap region or near a piece of debris on the surface. The figures shown here appear 2D, but they're actually side views of a planar fit to point clouds of one pattern center component plotted versus scan point position in X and Y. In the figure on the left, the X component of the pattern center is the vertical axis, while in the figure on the right, the Y component of the pattern center is the vertical axis. From simple geometry, it is expected that as long as the sample surface is planar, the X component should vary linearly with X position, and similarly the Y component should vary linearly with Y position. We can see that this is indeed very much the case. However, the astute viewer may notice that the variance in the fitted pattern center values in these plots is actually higher than in my consistency test on the previous slide. This is due to some slight effects on the fitted pattern center from the orientation of the crystal producing the initial pattern, as well as other possible issues such as lower power quality patterns near surface debris or grain boundaries. These figures nevertheless demonstrate the concept nicely, including its resilience to error in determination of any individual pattern center. All right, and so now we are coming up on questions. So as a reminder, please submit all inquiries through the questions pane, and thank you for listening to my talk. All right.
Thank you, Dr. Sparks. Does anybody have any questions they'd like to post? Please do so in the chat. We do not have any questions at the moment, but we'll wait a minute or two.
Give people a little time to type things out since they can't talk.
It was a very clear and concise presentation.
Thank you.
We'll wait just another moment for questions. So if you have a question, please get it into the chat. Okay, so here's a question coming in. Excess and deficiency lines, do they cause band location issues?
For the excess and deficiency, let's see, that's an issue with, so like one side of the pattern lines would be brighter than the other due to tilts. And as far as I can tell, they don't seem to cause issues simply because here I was testing precision based on just running the analysis on a set of patterns that should nominally all be the same orientation since they're all from the same spot on a silicon wafer, and then comparing that. And then when I run it on, say, let me pull up the previous slide here. So like here, this is essentially a randomly oriented polycrystal. And in terms of the noise, it doesn't seem to cause any huge issues when the orientation of the sample, like the orientation of the crystal being indexed, changes. You can, if you look closely, see a slight effect near grain boundaries where you start to get pattern degradation from more than one pattern being generated from the same interaction volume. Does that answer your question?
I'm not sure if we're going to get feedback on whether or not it answered, but a couple of questions came through, so let me continue with them. What is the speed of the algorithm compared to the Hopf transformation?
That is an excellent question. Let's see. I don't have a slide here, but the speed depends significantly on the conversion bandwidth. Using my relatively typical desktop for processing, it runs at a speed of about 20 patterns analyzed per second, which is quite slow compared to the Hopf indexing, which is fast enough to be used in real time while capturing patterns at 3,000 patterns per second. However, I have been informed that EDX is actually implementing this analysis method in a more efficient manner in their software, so that may improve things significantly, say up to several hundred patterns per second, which would still be slower than Hopf indexing.
Great, thank you. Next question, how does it work for pseudo-symmetric crystal structures?
Let's see, I have not personally tested that. However, Will Lenthe actually has a paper specifically on like predicting pseudosymmetry issues just from the simulated pattern center. Let's see, there you might want to use dictionary indexing possibly, which is even slower sometimes, but can more precisely match like very subtle differences in the pattern. Whereas at the conversion bandwidth of 123, the patterns are fairly like averaged out. the experimental patterns.
All right, thank you. And the next question is, how about magnetic fields distorting the acronym EBSPS? Not sure if that was typed correctly.
No, that's EBSPs, yes, electron backscatter
EBSP,
patterns.
okay.
I have not tested that, but, well, rather, I have not deliberately tested that. But again, this was tested on a nickel superalloy, which is at least somewhat magnetic. Let's see. I assume it would probably depend on the strength of the distortion. In particular, again, the dictionary and spherical harmonic indexing can be very robust to noisy patterns, but the precision would almost certainly decrease significantly. And it's a lot harder to characterize exactly how bad the precision is in, say, a deformed state versus an undeformed sample. Although if you have a magnetic undeformed sample, I suppose that could be tested.
Great, okay. So the next question actually begins with a comment. I love how the precision is improved. However, does this mean that the sample preparation must be much more careful for measurements like KAM?
Yep, that's pretty much exactly what I show here. You have to put significantly more effort into the sample preparation to ensure that you've removed all like artifacts from the preparation process, because now you can see things that you couldn't before.
And sort of connected, when using SHI versus the conventional Huff indexing to show lower misorientation with CAM, how valid is the process? How valid is the process data? And can you confirm that your misorientation is that low with techniques like neutron diffraction?
That's actually an excellent question. I have not tried that so far. Again, I've just been using like samples where the known level of deformation is very low, like the silicon wafer sample, various different silicon wafers, etc. That would be an interesting way of empirically determining how good it is. Let's see.
Great.
I don't personally have access to a neutron diffraction setup, sadly.
Well, that is the end of the questions. Thank you, audience, for asking some excellent questions. And thank you, Dr. Sparks, for the wonderful presentation on this indexing technique. We're now going to transition to the next presenter. Jonathan?
Thanks, Bill. Before I introduce the second speaker for today's webinar, I'd like to invite you all to register for the upcoming On the Scope, a masterclass in practical scanning electron microscopy. The program is hosted by the Ohio State University Center for Electron Microscopy and is sponsored by EDX. The course consists of two components. The first component will be held on May 1st to the 3rd and includes a series of lectures and demonstration sessions. It's 100% live, online, or in person. The second component is in person and includes hands-on training on the electron microscopes. This will be held in smaller groups with one session on May 4th to the 5th and another on May 8th to 9th. One thing we want to emphasize is the masterclass is not designed to overload you with slides in microscope theory. Attending does not require a background in microscopy to gain meaningful knowledge that you can apply immediately wherever you perform your SEM work. The course is structured to maximize hands-on experience. You'll be guided through the best practices of operating an SEM, from SEM alignment and imaging to chemical analysis in the SEM. More advanced SEM users will also have a lot to gain by attending this, as there are several advanced SEM topics covered. The masterclass is led by expert microscopists who you will have access to throughout the course. So no matter what level you're at, if you're aspiring to become better at SEM operation, this class is for you. The registration link can be found on this slide. Please note that the early bird discount ends on April 10th, but the registration will remain open until April 21st. And now I'd like to introduce Dr. Babu Viswanathan, who will be presenting the second talk in this webinar entitled A Few Compelling Examples of the Impact of EDS on Alloy Design. Dr. Viswanathan is currently a research professor in the Material Science and Engineering Department at The Ohio State University in Columbus, Ohio. Prior to joining the MSc, he worked as a senior research scientist at UES Air Force Research Laboratory, Wright-Patterson Air Force Base in Dayton, Ohio. Dr. Viswanathan is has considerable research experience, both experimental and theoretical, in structure-property relationship in structural and energy materials. Specifically, he has initiated and conducted research, both independent and collaborative, in the advancement of titanium, nickel, and iron-based alloys, intermetallics, and high-entropy alloys. He has decades of experience in analytical electron microscopy techniques in the areas of diffraction, high-resolution microscopy, high-angle annular dark field STEM microscopy, EDS and EELS, and X-ray spectroscopy and imaging simulation methods such as defect simulation and electron exit wave image reconstruction techniques. His research also includes the use of additive manufacturing methods for the development of titanium, nickel, and compositionally complex alloy systems. His collaborative research partners include government agencies, including the Department of Energy and Air Force Office of Scientific Research, and industries such as Rolls-Royce, General Electric, Pratt & Whitney, DNVGL, Chevron, and Exxon. Now over to Dr. Viswanathan.
Thanks, John. I think you're going to run the slides, I guess.
I just gave you access to the keyboard and mouse. See if you can advance them, please.
Okay. I'm kind of new. Where do I see that? I mean, to accept. Is this through webinar or? Okay, I think it's good that you run the slide. I don't have access to that. Can we go right? Can I go back? Yeah, it's a collaborative work. And first name is mine. Jake Jensen now is actually working for Thermo Fisher after graduating from here in Portland, Oregon. And then the third author, Brian Welk, is a researcher here, and with Professor Mike Mills and Henry Fraser. So kind of collaborative work here. And next slide. So these are most people obvious, but still I want to just go over this, the advantages of EDS. It's got a very high sensitivity, right? We can measure the concentrations up to 0.1%. These days is even better than that. It's kind of useful for detecting trace elements and impurities in materials. It's also very rapid analysis. In a few minutes, you can get a composition analysis or elemental analysis. And it's a non-destructive testing, so you don't have to really do much to the sample. You're not destroying the sample, except that it needs to be polished and then looked at it. And it's a spatial resolution from the olden days, from few micron and nanoscale. Now the spatial resolution and EDS techniques, depending on the probe they're using, it's up to few atomic spacing these days. So it makes it useful for analyzing materials at any scale. And it is versatile, the range of materials, metals, ceramics, polymers, and biosamples. But while there are many advantages for the EDS, there are also some disadvantages to this technique that should be considered. Limited elemental resolution. For example, if your atomic number is very close to each other, it's going to be difficult to distinguish. So you need some mathematical algorithms to distinguish between those two. For example, sulfur and chlorine, they pretty much overlap with each other. And EDS generate X-rays, which is a very sensitive sample, biological samples. You could damage the samples. And sample preparation needs to be conductive, so some non-conductive samples need some special preparations. and it needs to be done under vacuum, so it can limit the type of sample that can be analyzed. And calibration. This is the major part. EDS requires regular calibration to ensure your results are accurate. It could be time consuming, and unlimited depth resolution. EDS depth resolution limiting, which means that it can be only used from the surface of the sample. This can be a disadvantage with the layered materials, coated materials, and if elemental composition may vary with depth. But recent advanced EDS detectors have solved some of the problems, or mitigated, and some are minimized. So it's always progress over the years. Since I started my PhD 20 years ago, the things that can be done now could never have been imagined. This is a kind of industry-driven and user-driven as progress here. So with that, I'll start my quick presentation. I'm going to see, I've selected 3 topics that I thought could probably be sharing among, especially for allied design, for the metals people here. Because I'm a metallurgist by training, so I look at metals and alloys. So if I cannot finish all the 3, I can at least finish the top 2, which is so the first one is it's a nickel-based superalloy. It's been subjected to very high oxidation environment. And we'll see, and EDS has really helped to locate where the compositional and structural instabilities occur. I'll give some examples of that. And the next one would be a high entropy alloy. This is the high entropy alloy has been in the business last 10 years or so. It's got a very high potential to become an aerospace alloy for high temperature applications. And we use this EDS tomography to develop some morphological descriptions of the precipitates. The last one is we can push this EDS techniques to atomic scale segregation, and which is actually leading up to some of the design of the new class of aero engine alloys. So I'll share some of the results that we have. All this work was done at Ohio State in CEMAS, and with the help of all the EDAX detectors and other EDS techniques that we have here. So let's go to the first topic. For example, this is the aircraft material. Use the one in the center that you can see, the shaft, disc, and blades. This is a typical aero engine disc alloys. It actually reaches a temperature of about 700 to 900 degrees centigrade, depending where it's on the engine. Sometimes, if the material has a defect for some reason or other, the disc in the middle could break into, and then it can shatter the engine. One of the examples shown on the right side is where one of the parts of there was a real accident in the aircraft industry that happened quite a few times in the last 10, 20 years. So disc failure is very rare, but it's not that uncommon. That the failure could be due to several reasons. One of them is an impurity level, or some of those levels, internally there could be some oxidation. And that's what I was going to look at on this. This is a industry-funded project which went into atomic level type of work. So I'll share some of the experience with that. So next slide. So this is a typical nickel-based superalloy microstructure. The dark areas are the hard precipitates, gamma prime precipitates. And usually nickel-based superalloys have several elements, at least eight elements they add, and depending on the temperature, stability, and where they want to use this. Mostly the gamma prime precipitate, which is darker regions that is shown in the micro, is where the strength actually comes from. The strength also depends on the distribution, size, and the volume fraction of those precipitates. So this is the microstructure for this alloy that we have been examining. Next slide. It's a probing regions ahead of advancing crack. Next one. Suppose if a component has a crack along the grain boundaries, and then the cracks can extend. As the crack extends, the oxygen can get in those cracks, and it can start oxidizing those elemental in the alloys there. So what you see here in this picture is that you see some of the open cracks, and right at the crack tip, the oxides have not fallen out; it's still embedded in it. If you can somehow get ahead of the crack and prepare a TEM foil, and see what are the changes to the compositional instability because of the oxygen reaction to that. So we could probably get some idea about why and what elements are actually suffering the most. So that is the crack path that was investigated for this portion of the talk. And if you look at it, that on the right side image, the arrow is where actually the compositional analysis was done from the open crack to the closed crack, but still oxidized and far ahead of the crack itself. So this is an open crack, heavily oxidized. You can see those lighter edges or the oxygen rich. So it's a HADAF image that shows a lighter average atomic number contrast. As you go inside the crack, you start oxidized, but the oxides are still intact. And if you further go a couple of 3 to 10 microns, if you go into along the boundary, then you can see this oxidation. It's not the visible oxidation has not happened yet, but you can actually capture the very early stages of oxygen damage in the rightmost image that you can see. We'll discuss that in a quickly. Next slide. The elemental segregation oxidation. So this EDS techniques with the resolution that we have, with the high resolution that we have, we can actually map. On the left side is the HADAF image, and the middle and the right is aluminum and aluminum oxygen. So you can, if you know the composition of the alloys, you can actually map out where that element is. Next one. So you can see from the top in the middle, you can see the chromium is the most oxidizing element, right? That's the blue region there. But you can actually pick up where the segregation of these elements is happening. The next slide. On the left side is just a HADAF image of oxides. On the right side, now you can start, if you put all the elements together, and you can get an idea about what is going on there. So the next slide is the same one that we had it in the previous slide. Now you can see right next to the bulk material, you start developing a thin aluminum rich layer, followed by a titanium rich layer. And the blue is the chromium rich. And in the middle, where the oxides are really filled up the cavity, is a nickel cobalt iron rich. So very close to the surface is where the aluminum is. Let's focus on that for a second here. Next slide. And then you move away from that fully oxidized towards the interior of the bulk. You don't see the bulk oxides there, but oxygen has traveled through the grain boundaries. And you can see that in the bottom two, the aluminum is the element that actually segregates to the most with oxygen in there. So the very thin layer, that is the kind of a beginning of your oxidation. So aluminum is the one. Where did the aluminum come from? The aluminum comes from those little round particles that you see, gamma prime particle, which is a strengthening particle. And if the aluminum tends to leave the particle, migrates to the grain boundary here. So that's the thing first thing happen. And the line analysis shows you that there is an increase in aluminum and oxygen across the interface. And if you want to probe a little further into the region ahead of this line, you can actually see how oxygen percolates through the bulk material and access the aluminum from those gamma prime particles there. So you can see the aluminum and oxygen elemental mapping. You can see those the dark areas where near the boundary where the gamma prime particles were there. Now it has lost its aluminum to the boundaries because of either oxygen is seeking the aluminum or aluminum is seeking the oxygen, but eventually aluminum ends up at the boundary. What happens because of that is because you lose aluminum, you lose the particles near the boundary and you lose the strength. So now the boundary near would lose the strength and the crack can advance further and further. So this was the first time ever shown this gamma prime particle, the strengthening particles in this alloy is actually dissolving because of the oxygen. And some other images that I showed, that's a schematic of how that occurs. So basically those little particles near the boundary dissolve. When I say dissolve, the aluminum is going away into the boundaries. But it's got a very simple explanation. So people who have done some chemistry and physics would know that the partial pressure is dependent on the element, depending on the partial, the oxidation kinetics of the element depends on the partial pressure. Since deep inside the crack along the boundary, you don't have much of oxygen, so only certain elements can oxidize under that partial pressure. So aluminum is a candidate. The diagram that you see on the right says the Elegance diagram. So aluminum is most likely to be the oxidizing agent, and that's what seems to be happening here. So in terms of oxidative sequence, aluminum oxidizes first, titanium, then chromium, then cobalt, and nickel. And now we have a full picture of how this the oxidation sequence happens, the buildup of oxides. The result of this is that initially it was thought the crack goes from left to right. That means you oxidize the surface and it weakens the materials and you start cracking along the grain boundaries. But actually it could be partially different. It's the segregation of aluminum to the interface far ahead of the crack happens much earlier. And the crack actually micro cracks can form before the visible crack, and they can line up and then they can break the materials. So this has been published many times. This project was done with the help of Rolls-Royce. So some of it is private. So the private in the sense is not all the disclosures can be done on this, but this is the published material. Next. Second topic is a tomography of some of the morphological descriptions of a precipitate in a high entropy alloy. Next. The microstructure you see left on the side is very similar to what nickel-based superalloy you would see on a single crystal blade alloys. But this is a different composition. We call it inverted superalloy because the dark regions in those micrograph on the left side is the ordered region. The precipitates, which is lighter regions, which is kind of square looking or plate looking ones, or the BCC, which is a disordered. Normally in superalloy, the case is reversed. And that is the reason this alloy has got so much interest, because this alloy seems to be having some kind of what we call ductility in our world, even though the darker regions, which are ordered regions, tend to be brittle in other alloy systems. So the exact composition of the alloys, we are able to, now many people have done this in many other institutes and places, but we were one of the first earlier ones to measure the actual compositions of those precipitates. So on the right side, you can see the lighter region, the cube regions are enriched in tantalum, niobium, and moly. But the channel, the B2 phase, is enriched in aluminum, titanium, and zirconium. So those are quick results coming from the EDS analysis. The next. But by looking at the HARAF images, or even on the SCM, if you look at it, we don't know exactly the shape of the precipitates, but they're all cube looking or a plate looking. So normal tomography in a single tilt series would limit our observations here. So what's the true morphology and distribution of the faces is probably unknown. It cannot be determined by single teat. So a technique was needed to eliminate the normal problem that we have with the tomography, which is missing wedge and pyramids of information. So we need a larger tilt. So next slide. So we prepared an atom probe-like needle, but it's not that small, but it's much longer. We can prepare sample up to 100 micron in length. So we use focus ion beam to fib a region of interest, and then we prepare this tall needle that you see on the right side, high entropy alloy, the same alloy that I showed before, previous slide, and then we thinned it just like we thin an atom probe, and we have a holder here at the FEI. Now it's Thermo Fisher holders and Fisciani holders, so we can use a different type of holder and start imaging this in the TEM. So you can see the top, you can see those square precipitates in the needle. It's about 100 micron long. And we can rotate this needle 360 degrees. So we probably need about 180 degrees at the minimum to know where the morphology of the precipitate. So go ahead, next one. So this is the final results from the tomography. The EDS analysis, the X-ray was captured, and then this is the segregation that you would have otherwise normally seen in a 2D image. Now we have a three-dimensional mapping of those, the elemental segregation. Next slide. Can you click on it? Yeah. So this is how the tomography was done. Visio was used to segment those. On the top is just imaging segmentation. The bottom is the EDS tomography of the nail. Stop that. Next slide. So when you, in the top images that when if your HRF is sufficient to resolve the vein fine precipitates, then you can go with that. But sometimes the precipitate HRF resolution is not enough. The EDS gives you the much better analysis. From the top image, you can see on the right side, that's what we had on the two-dimensional image. We thought those were all like thin plates, but it happens to be a mixture of a cube next to plates. Both are very similar compositions, the same composition, same crystal structure, but some of them are forming tubes, some of them are forming the plates like. So this is a very useful technique to get the morphological and then the EDS also, the fine precipitates, we're able to do this. And this has a huge implication on how this alloy would coarsen and then would behave in real high temperatures. In the same alloy, if you look at the top one, this is the SEM EDS mapping. You can see those in the middle, aluminum, and the right side should be zirconium. Red one should be zirconium. So zirconium and aluminum, they segregate to the boundaries, which was limiting the ductility of these materials. And we didn't know that in the beginning until we found out that what kind of, so the EDS helped know initially what are the compositional there. And based on that, we did some diffraction work on the left side on the TEM. So we determined what is actually the crystal structure of those precipitates. And we could take all the way to the high resolution image. We know exactly the structure of the precipitates. So the whole point was that in this case, the EDS analysis helped to locate the source of brittleness in this alloy. So now we are in the process of developing an alloy which would avoid this precipitates and which would make it more ductile for applications. And the last topic probably I'll go through so using a combination of CBED, which is a diffraction technique, EDS, atomic resolution, we could figure out without EDS, we could not have actually done this process identifying the middle phase. So it's something very small that you would start with would end up with a huge implication for the industries. The next one. The last one is atomic scale. This I would have just one slide for this. So sometimes if you look at on the left side, this we did in 2015, which is an alloy, the super alloy. You see those lines running from top to bottom. Those are the stacking faults. So this is a very simple observation. While we are routinely doing the compositional mapping in those days, we didn't have a very high resolution capability at that time. And we found that some of the elements are segregating, some of the elements are leaving. In this case, chromium is segregating to the stacking faults, those little lines running from the top to the bottom. And we didn't think much of that anyway at that time. Then we saw similar looking segregation of not only chromium and cobalt, but other elements either segregating to the stacking fault or leaving the stacking fault. So more and more super alloys were identified to have the same stacking fault do form during the deformation of these alloys. And when the resolution of the microscopes improved, we could actually see what is happening in the stacking fault. In the top image, ME3 to 2020, you can see the stacking fault where you can see this heavier elements glowing as lighter atoms. And now we are in a position to see what atoms and where it is segregating. And it's segregating to 3 or 4 atomic spacing level. And locally, it actually changes not only the composition, but also changes the local crystal structure. And now this is termed as localized phase transformation. That's because the crystal structure has changed, composition has changed. So this little precipitation kinetics on the stacking faults, it has huge implication on high temperature creep properties, mechanical properties in the alloy. And now we're using this to our advantage to design, put back that diagram. The alloy, yes. So we're using this thing to narrow down some of the alloy composition. We would like to have it in the middle of this diagram. You can see LPT alloys, and those, some of them have shown to be having a higher mechanical properties. So some of them are being tested and developed in the aero engine companies, and this is the last 10 years or so. This has been one of the focus for some of us who are involved in this kind of research. So basically, what we are doing is that the segregation to the stacking force, we're making use of it to design stronger and stronger alloy that would operate at high temperatures. And with that, I would close, and I'd like to thank MSc, then mainly CEMAS and the CAM, the center that some of this work was done. And for these 3 topics, we collaborated with Rolls-Royce, GE Aviation, and of course, Office of Scientific Research. And we thank EDAX and Gatan for their useful detectors, useful instrument, advanced technologies for helping this happen. Thank you. I'll answer questions if there's any.
Thank you, Dr. Viswanathan, for a presentation that has implications for us all. That was very interesting. Please send in questions. At the moment, I do not see any questions have posted. But audience, please do send some questions so we can continue the conversation for another moment or two. We'll wait just another moment here for your questions. Okay, here comes a question. Does ion implementation cause issues? For example, phase transformations?
Yeah, that's a good question.
Sorry, to substitute a word, does ion implantation, not implementation, does ion implantation cause issues like phase transformations?
I'm assuming that ion implantation coming from the focused ion beam, the sample preparation, I would assume that. And in this, the preparation of the first part of the talk was, I mean, I'm assuming is that what the question is about ion implantation. Is it coming from, if there is a contamination from the fib, which is a gallium source in this case, you could always pick up some gallium. And with that, some oxygen could come with that too. So which is of less importance. It may be important to detect whether gallium or whether oxides are, but it won't change the kinetics of at least the first part of the talk, where there is the oxygen kinetics are there. And of course, in the high resolution atomic resolution image, the samples are pretty much cleaned after the nanomilling, what we call nanomilling. It removes some of the amorphous layers caused by either gallium or amorphization of some of those elements. So there is definitely an effect of the ion damage from the sample prep, which are minimized by low kV milling of the samples before the characterization is done.
Okay, thank you. Another question came in. I think this is a bit more of a general question. What is the most precise form of EDS scanning in the SEM? Point, line, or area under high magnification?
Yeah, that's a very good question. Actually, that's as a user, like all of us know that it's a beam, the type of resolution that you want. If you want to go for a very high resolution, you go for low beam current, low beam size. And also, if you have to adjust the voltage, because the larger voltage gives you the larger depth, sometimes it will interfere with those the precipitators or whatever lying below the surface. So depending on what you want to do that, but I would say it's in my thing, if it's a small precipitate, I'd like to go for a line scan first to get an idea, very quickly an idea. The area scan, sometimes you'll run into the issues that the samples are partially charging or fully charged. The images would shift, even though there are cross correlation methods for each pixels. And the SEM is not as well developed as in the TEM level atomic resolution, where the algorithms have become able to track the same atomic column over sometimes minutes. Actually, you can track it. So if you're a beginner, I would just go with a spot analysis, a line trace, and then prepare a map and control your shift, the scanning errors. Right. And then again, it depends on the size of the precipitates, because then you have to adjust the voltage. You don't want to be having very high voltage. You'll be sampling beneath the precipitate that is at the top.
That's a great question for the SEM masterclass. If I could get a final plug-in for that. Okay, I don't see any more questions. So with that, I want to thank our presenters, Dr. Sparks, Dr. Viswanathan. Thank you, audience, for attending. Have a great rest of the day.
Thank you. Thank you, Bill. Thank you, John.
Thank you.